So today in this lesson, we're going to be focusing in on linear functions. So the first section of our foldable. Go ahead, and if you're following along, write down our standard, which states that students are going to be able to graph a linear function, express symbolically, and show key features of the graph. Now, this standard is going back to what we did earlier this year. We were able to take functions and rewrite them in many different ways. We focused primarily on quadratics this year, but we still need to remember linear functions from Math 9. So, this is our function standard interpreting functions. And we're going to be able to do this for all of our different types of functions, as we saw on the foldable title. Linear functions from last year in Math 9 are straight lines. That's what linear means. So if we take a look at the basic function, f of x equals mx plus b, we have a straight line going from left to right in an increasing fashion. This happens when we have a positive slope. Remember, in slope-intercept form, m is our slope, and b is the y-intercept. Those two values are the only things that we actually have to know in order to graph a linear equation. Now, this year we learned about quadratics. There are a lot of extra things we have to know about quadratics. Linear lines, though, we don't really have to do much other than slope and y-intercept. Take this example. What we have here is f of x equals x minus 4. It's a very basic slope-intercept form problem. We see that we have an xy chart already set up with -2 starting and 2 ending. And our job is simply to plug in our x values into our function. So, we need to take this -2 and input it into our x value. We end up getting -2 minus 4, which gives us -6. If we follow the same process for each of our values, we get that the next one is -5, next one is -4, -3, and -2. Moving up 1 each time. That's why this is a linear equation. It's going up by a constant rate each and every time. We can now go over to our graph and plot each of our points. So at -2, -6, -1, -5, 0, -4, 1, -3, and 2, -2. We get our line as we connect our points, and we've graphed a linear equation. Now, this right here is something that we would have seen last year in Math 9. We take our slope-intercept form problem and plug values in. What we're going to take a look at today is domain and range. How this idea of a linear equation can actually produce different domains and different ranges compared to other types of graphs. These two definitions here are the only definitions in this foldable, or in this section, sorry. We have domain. We're talking about all the possible x values that produce a real number. The range is just the y values with the same definition. All the possible y values that are produced by the equation. So a nice way to think about this is, for domain, what x values can you plug into the equation? Well, the answer here is all real numbers. And this happens because you could plug in the number 500 and you're still going to get a real number. You could plug in a negative. You could plug in a radical. Doesn't matter. You're still going to be able to get a real number value. And in fact, for linear equations, the range is also going to be all real numbers. Linear equations are like this because we're going up and down in a straight line. Always moving, never actually stopping. So for linear equations, both domain and range are going to be all real values. Now, we need to take a look at domain and range. Domain and range are going to be used throughout this entire foldable. We're going to be focusing in on what x values we can use and what y values we can use in our function. So, as our first definition, domain, it's all the possible x values that produce a real number in our function. This could be anything. It could be a radical. It could be a negative number. It could be 1 million. It could be any x value that produces a real number. For the range, we're taking a look at the other side of that. We're looking at the possible y values produced by the equation. So for instance, in our function we just graphed, x minus 4. Think about the x values you could plug in. You could plug in a fraction, a negative, a radical. So for this, our domain is all reals, or all real numbers. If we think about all the possible x values you could plug in, think about all the y values that are possible. And we get that the range is also going to be all real numbers. If we look at the picture of a graph of a linear equation, we have a straight line going like this. The arrows on each end of the line signify that it doesn't stop at that point. It actually continues on and on, telling us that no matter where we are in the graph, we're still going to get some x value, and we're still going to get some y value, all real numbers. We're now going to take a look at one last example, and this one is a combination of things we did last year and things we're going to do this year. What we need to do is be able to take a table and write an equation from the table. If we recall, for a y equals mx plus b problem, we need two values. We need m, which is the slope, and we need b, which is the y-intercept. The y-intercept of a linear equation is when x is 0, thus b in this case is 1. We also need to take a look at the slope. We see that the x values are going up a constant 1, which means we can just simply figure out what are we adding or subtracting each time in the y values. To get from negative 7 to negative 3, it's a plus 4, and we see that that's consistent all the way through, making our slope 4. Once we have m and b, it's simply a matter of plugging in the values into their appropriate spot, giving us a final equation of y equals 4x plus 1.